So that was just a pre-lecture, imparting of information. Right, so today we're going to begin the fourth part of the course, which is about biogeochemical cycles. And biogeochemical cycle, biogeochemical is one of these long words that scientists just mash together, lots of different terms, make a long word to make them sound impressive. But it's basically the interaction of biology, chemistry, and kind of the solid earth and geology. So bio, geo, and chemical. Okay? So we're really looking at how key elements for life move around different parts of the earth and either become available or unavailable for life. And those key elements are carbon, to a certain extent oxygen, won't reduce much in oxygen, and the nutrients. And the nutrient elements are basically things that life needs to survive, but only make up quite a small part of the actual biomatter. Okay, so biological material is mostly made up of carbon, nitrogen, and hydrogen. It's also got other stuff in it that you need. So things like nitrogen. Okay, so nitrates are a nutrient that if we don't have any nitrate, we can't grow any life. So we can't grow plants. We don't have amino acids in us, and that would be bad. Similarly, elements like phosphorus and sulfur, also critical for life. Okay, and we're going to be looking at how those elements are moved around different reservoirs in Earth. Okay, we'll go on what I mean by reservoirs mostly today, and how they determine where life can happen. Okay, so this kind of tries to kind of bring together some of the stuff you did with Steve. Okay, because the development of these biogeochemical cycles, the availability of nutrients was critical for the evolution of life. Okay, so today we're basically going to just look at what are these different things that I'm referring to as reservoirs. So different places in the Earth system where there are different, basically, physical chemistry environments. Okay, so for instance, the atmosphere is a gaseous environment. The ocean is an aqueous environment. So we're going to be looking at these different kind of boxes of the Earth system where kind of we can put chemical elements and do chemistry with them. Okay, you should be familiar with chemistry from Brian's lectures, which were good, right? Right. Okay, so we start off with the atmosphere. So quite a lot of this will be kind of fairly noddy, straightforward stuff that you should be very familiar with, but the atmosphere has been with us for quite a long time. It's not been the same throughout all of Earth's history. We lost it at one point. It's very unfortunate to lose the atmosphere. But fortunately, it came back. It wasn't the same atmosphere that came back. But that was very early in Earth history. And it's really important because it controls the climate. Okay? So the balance of gases in the atmosphere determine the temperature of the surface of the Earth, which keeps it habitable. Okay? So you should be familiar with that from like the second part of the course, my first part, the second part. Okay? Another thing about the atmosphere is that it's really, really well mixed. Okay? Because it's heated from the bottom. Okay? So it convects a lot. So it's you can kind of think of the atmosphere for most things in the atmosphere. It's almost completely uniform in terms of its chemical composition. And that's not true, okay? But for most things, we can kind of at this level we can think of it as really, really well mixed. Tell these guys about the stuff on Learn later and all of the secrets we were giving out about how to do well in the practicals. Right, okay. Yeah, because it's well mixed. If there's an atmosphere, so this last statement at the bottom is that because it's really well mixed. If something changes in the atmosphere, okay, that's a global change. That's affecting almost everywhere on the planet. So you can think of the atmosphere as kind of globally integrating signals. So just to quickly kind of go over the structure of the atmosphere. So it's got lots of these layers: the troposphere, stratosphere, mesosphere, thermosphere, ionosphere, and all this kind of stuff. These other spheres in the atmosphere. But the key thing is that I guess you can't. It's quite hard for you guys to make out the actual scale on these this graph here. So I'll just see if I can point this out. So these are height above. This is the ground here. This is height in kilometres. Okay, and it goes 10, 20, 30. It's a linear scale. Okay. This axis over here is pressure. I mean, the units are millibars, but it should really be in pascals if we're being all, SI units. But you'll notice, hopefully, if you can just about make this out, this is 1,000 millibars, 100 millibars, 10 millibars, 1 millibar, 0.1 millibar. This is a logarithmic scale. Okay, so that means that all of the pressure is down here at the bottom. It's kind of, you'd expect that with the pressure is because it's got the atmosphere on top of it pushing down. That's why we have atmospheric pressure. But this means that almost all of the mass of the atmosphere is at the bottom. Okay, so almost 90% of the atmosphere is within this troposphere at the bottom. Okay, so that's where the important kind of radiative forcing really goes on. But there is some interesting chemistry that goes on higher up in the atmosphere where we have more intense solar radiation. Okay, 'cause it's not protected by the atmosphere because it's on top of the atmosphere. And that causes some photochemical reactions to happen, interesting stuff like the degradation of ozone, things like that. But the key thing is most of it is down in the troposphere. The next layer up is the stratosphere. And the cool thing about the stratosphere is that it is stratified. So if you look at the temperature profile, okay, you can see that it's warmer at the top of the stratosphere than bottom. Okay, and that's because it's actually being heated from the top. Okay, so the heating in the stratosphere is actually through mostly the absorption of shortwave radiation, okay, by ozone. Okay, so this is the ozone layer. It's not really a layer; it's the whole atmosphere has got lots of ozone in it. And this causes it to be very, very stable. So it doesn't want to convect vertically. Okay. So once you get something into the stratosphere, it tends to stay there for a very long time. It doesn't get mixed out so easily. And then on top of that, we've got this other stuff, thermosphere, mesosphere, pretty kind of irrelevant to the total mass of the atmosphere because the pressure up there is so low. This is where kind of like cool stuff happens, like radio waves and the aurora and all this kind of stuff, which you should be familiar with if you live in Scotland. Okay, so composition-wise, the major gases in the atmosphere are nitrogen, oxygen, and argon. Argon is completely inert and is utterly irrelevant to almost everything, unless you're an argon geochemist, then it's massively important. But yeah, so the key things is that some of these elements, so nitrogen in particular, is key to life. Really important for us to have nitrates. But the form that nitrogen is in the atmosphere is this N2, and you should know that that's a triple bonded covalent molecule, so that is extremely difficult to break apart. So N2 is not very useful to life, so stuff must happen to that to make it useful. And we'll go on to that in the nitrogen lecture. Oxygen, I mean, it's quite handy if you want to breathe. It's actually very toxic to life, but nonetheless, it forms a major part of the atmosphere, which is fortunate for animals. There are also some minor components, and there are lots and lots of these kind of like minor gases. It's not just CO2 and methane; it's nitrous oxide and other gases, CFCs, all this kind of crazy stuff. These are very, very small components, but they're important because they're important for the radiative balance. So they're important for this kind of regulation of the temperature of the Earth. Okay. And it's not just gases. So this is kind of where we start to interact between the atmosphere and some of the other spheres, so the biosphere and the lithosphere. So we do have some of the kind of the Earth's crust, so the lithosphere, rocks. Some of that is ground up into very small particles and blown up into the atmosphere. Okay? Some of it is directly injected from volcanoes. We get volcanic ash up in the atmosphere. I mean, some of this stuff is suspended all the time. And then we have other things, organic particles. So this could be when natural forest fires, or actually some plants give off volatile organic compounds which condense and form aerosols. And these are important for the reasons we went through in the climate lectures, especially for things like cloud condensation nuclei. Okay, so these determine whether you would get clouds or just water vapor. They determine how white the clouds are, how long they last. Okay, so these are important climatically. Okay, they're also important for transporting nutrients around. Okay, so it turns out that in some regions of the Earth which are really depleted in some of these really important nutrients like nitrate and phosphate, sometimes other elements which are critical for life like iron. Okay, so you might, your mum might make you take vitamins to like keep you healthy, and those vitamins contain kind of lots and lots of elements: zinc, iron, cobalt, all these kind of things that you think, oh, I should have that in my diet. Okay, these are you have them in your diet because they're important for life. They're important for functions. Make sure your enzymes work. Okay, keep you alive. So life does need these kind of really small quantities of trace metals, and some of these trace metals are transported around the Earth from areas that don't have them, from areas that do have them, to areas that don't have them, by some of these dust particles. Okay? So that's important. So dust is important for micronutrients. So we call these elements which are kind of, you need them in very low concentrations like iron, zinc. We call those micronutrients because they're less important. Well, they're just as important. You need them, but you don't need them in lower quantities than the macronutrients, the major nutrients: nitrate, phosphate, sulfur. Obviously, we've also been playing around with the atmosphere, kind of doing some experiments by burning lots of stuff, and that creates lots of aerosols that go up to the atmosphere. Also creates lots of atmospheric gases that weren't there before. Okay, so moving on to the next sphere. So that's kind of the atmosphere. Put the atmosphere away for a while. So the lithosphere is the solid Earth, the bit that you should be interested in if you're on a geology degree, or a GPG degree, or even an environmental geoscience degree. The lithosphere is really important. If you're only interested in the the biology bit of Earth, or the ocean bit of the Earth, you still have to consider the lithosphere. The lithosphere is kind of like the basin in which the ocean is kept. Okay, it's also kind of the thing that life sits on. Okay, so it's constantly interacting with the biosphere through soils. Okay, it's also interacting with kind of like the hydrosphere, so the oceans and rivers and lakes, through weather influxes. Okay, so this is we're taking elements out of rocks, we're weathering them, and we're putting those into kind of the environment where they can be used by life. It's actually, life can happen inside rocks as well. So if you dig down deep into the crust, you actually find bacteria that kind of like eat away at the rocks without any other kind of like interaction with the kind of like traditional, more biological environment. But that's a very small component of it. Actually, it's a very large component by mass. Okay, so there's an enormous amount of biomass deep down in the earth in rocks, but it works very, very, very slowly. Okay, so it's not hugely important in terms of the global amount of biology produced every year. Anyway, and it's really heterogeneous. So we kind of covered a basic heterogeneity between, I think the next, no, it's not. Never mind. So some of the rocks, for instance, are carbonates, some are silicates. And when you do the same chemical thing to those, if you kind of like add water and try and weather them, you get very different results. Okay? So you get either a congruous weathering or an incongruous weathering, which if you read those papers, you might have some idea what that is. But basically it means that one draws down CO2 in the long term, the other doesn't. Okay? And you can see here that like the lithosphere is made up of all of these kind of like rocky elements. So these are elements that are commonly found in rocks, so things like silicon, aluminium, iron. So these are things that kind of traditionally make up kind of silicate rocks. You can think of this as maybe the composition of some kind of basalt, for instance, containing minerals like olivine, which is an iron, manganese, iron, magnesium, silicate. Also things like minerals like feldspars might have potassium, sodium in them. Okay, so this is kind of like where all of these different these are the elements in rocks, and some of these elements are really important for life. For instance, phosphorus, particularly phosphorus. So phosphorus doesn't really come from anywhere else but rocks. Okay, there's no phosphorus in the atmosphere. So the source of phosphorus from rocks is really important, and we need phosphorus, phosphate, for life to exist. It forms kind of the ends of molecules that make up all of our cells. So if we don't have phosphorus, then cells wouldn't really work, which would be bad for things made out of cells. Yeah, so just to point out again, these different types of weathering, mechanical and chemical weathering. This kind of chemical weathering. It's the chemical weathering that's the kind of like what matters for life, because that's the thing that actually releases these elements from the solid phases, okay, and releases them into the environment. You can use them, and there are these really important. So chemical weathering is aided by mechanical weathering. So this is kind of thing on long geological timescales. It is important to have mechanical weathering because that grinds up the rock into smaller particles, increases its surface area, and increases the rate of chemical weathering. This is kind of a little bit of an aside, which kind of like might bring you back to a little bit of stuff you might have done in Earth Dynamics, if you're on that course. Is that rocks are made up of lots of different minerals, and the type of mineral a rock is made up of is important for determining how fast that rock will weather, and also what its climatic effect will be. So if you have rocks that are made up of these minerals up here, olivines and pyroxenes, okay? These are rocks which are typically formed at higher temperatures. Okay, so these are the kind of rocks you might expect to have in basalts, gabbros, okay? You might find these kind of minerals out in, certainly the pyroxenes maybe out in, on Arthur's Seat. And those minerals are quite far out of their equilibrium temperature. So they formed at very high temperatures, so that's kind of where they're happy. But they're now maybe at the Earth's surface where it's nice and cold, and they're basically quite meta-stable. They don't like being cold. So they weather quite quickly at the Earth's surface. And also these minerals are quite simple. Okay, so if you think about the structure of olivines, it's a simple magnesium silicate. Okay? So when it weathers, it completely dissolves. Doesn't form any clay minerals. So that's a congruous weathering. Okay, where the end product is chemically identical to the starting product. So that adds all of its elements into the ocean, whereas some of these minerals over on the other side, which I shall point out with a little thing, these guys, so these are plagioclases. Oh, well, that's a plagioclase. This is a orthoclase, I think. No, is it? Sodium rich. Oh. No, it's not. Anyway, so those are all plagioclase feldspars. These potassium feldspars are orthoclases. Don't listen to whatever I say on minerals, okay? I know very little about minerals. Anyway, but those minerals, when they weather, okay, they tend to form in slightly lower temperature igneous rocks. So they're a little bit more happy at the Earth's surface. So they weather a lot slower. They're also made up of more continuous silicate kind of frameworks. Okay, so they're built they're based on framework silicates, whether these are ring or single tetrahedra silica or a chain of silica tetrahedra. They're easy to break apart, whereas some of these feldspars are more robust, they're harder to weather, so they weather more slowly. But when they do weather, they also kind of like have intermediate weathering products, like clay minerals. Okay, so this is incongruous weathering, so you get less of an effect, you release less stuff ultimately into the dissolve phase when you're weathering rocks made out of these white boxes. Okay, so the composition of what you're weathering matters, is the take-home message really from the slide. And you'll recall from the lectures when we were talking about feedbacks in the climate system that there is this really strong feedback between climate and weathering. Okay, so when it's really, really wet, and when it's really warm, so this is quite a difficult to understand graph. So we just kind of talk to it. So this is, you can think of this is a plot that's got three axes. So the higher up you are on this vertical axis here, this is the silica flux. So this is the rate of weathering, the amount of kind of elements we're releasing from rocks into the dissolve phase. So the bottom 0 is no weathering, 8 thousand, was it moles per hectare per year? Some really kind of convoluted kind of unit, but this is kind of the amount of stuff you get out of a field. Okay, so that's quite high, and that increases as you increase temperature. So as you go from 0 to 20 degrees, if you just look at the back axis here, you can see that ramping up. Okay, so you get much higher rates of weathering when it's hot. Okay, that's because chemical reactions are temperature dependent. Okay, you should remember the Arrhenius equation from Brian's lectures. Okay, we've got E raised to the power of something times K with a T in it. Yeah, I can't remember the exact equation, but you should know it. Yeah, and also when you increase the amount of water. Okay, so when you increase the amount of water, you increase the amount of weathering. Okay, and actually, talking about the Arrhenius relationship, you can see that the relationship with temperature is curved. Okay, so it follows a power law, which is what the Arrhenius kind of reaction rate equation is. Okay, and importantly, okay, and this, we'll go over this in the carbon-themed lectures. There's this when you weather silicates, you draw down carbon dioxide, but when you weather carbonates, you don't. And one of the key things to consider when you're talking about the carbonate system is that it's not just, we're not just talking about carbon. When carbon dioxide is in contact with water, we have this two-stage, that is wrong. Nobody write down that equation, because that is disastrously wrong. Actually, so when water and carbon dioxide, they react together to form this guy over here, okay, which then dissociates into this guy, which is bicarbonate and a hydrogen ion, and then that dissociates again to carbonate, which is just CO3 2 minus and another hydrogen. I will fix that for the carbon lectures. Sorry, but the important thing is that this allows us to store lots and lots of carbon in water, okay? Because this reaction in most systems favours the formation of that middle compound bicarbonate, so we can build up enormous concentrations of carbon dissolved in water and keep the actual concentration of CO2 dissolved in water very, very low. So very little can interact with the atmosphere, okay? So it means that we can, if we, for instance, have some water, kind of like in soil, so soil has got lots and lots of kind of moisture in it. That soil has got lots of organic matter in, that respires, so it starts to degrade that organic matter, which is essentially the same as burning it, but in a non-kind of flamey way. And that releases lots of CO2 into the water, okay? That CO2 is converted into this mostly bicarbonate form, okay? And you can see that that produces a hydrogen ion, okay? So in soils, you can, because you're constantly adding CO2 from the respiration of organic matter, you build up enormous concentrations of carbon dissolved in the water. That causes there to be very, very high concentrations of this bicarbonate ion and also high concentrations of hydrogen ions. Okay? Which means that makes the soil water more and more acidic. And that helps dissolve the rocks. Okay? So that increases the rate of weathering and then increases the availability of nutrients. So you can kind of, so that this, ignore the equation at the top of there, you can kind of see that's happening in this figure here. So this is some limestone pavement, and you can see there's no soil that you can see on the surface. Yeah? But actually, in these cracks, I think they're called grikes, but let's just call them cracks. You can see there's little, it's actually a beer can there. You can see lots of plants. Yeah? And there will be a very, very thin layer of soil underneath those plants. Okay? And there will be some decay of organic matter in those cracks. Okay? That's concentrating carbon dioxide in the water that's up against the rock that's held in these cracks. Okay? That's causing there to be much, much more bicarbonate, much, much more hydrogen ions. Okay? That's what's dissolving the rock. Okay? So although this looks like the rock is being dissolved by kind of rainwater flowing over it, it's actually being dissolved because soil is forming in cracks, and that soil is very, very high in dissolved carbon, which causes it to be acidic. So that's what's causing the dissolution. Okay. I guess this slide is less important than some of those. Just to point out that you do have chemical weathering and physical weathering, and you get different proportions of those depending on where you are on Earth. Okay, so if you look at some of the ratios here, if you look at continents that have got large mountain ranges, lots of active uplift, that causes there to be lots of physical erosion. So places like South America, where you have the Andes, and Asia, where you have the Himalayas, you have quite high rates of mechanical weathering, or mechanical erosion, okay, and relatively low rates of chemical weathering. You still have quite high rates of chemical weathering. That's because Asia is really big. Okay, so per unit area, it's kind of low compared to the per unit area of mechanical weathering. So you can see the ratio in these areas is really high. Whereas places where there are not lots of active uplift, Africa, Europe, I mean it has the Alps, but you know that's small time. Australia, lower amounts of active erosion. So these are places where there's less overall weathering, okay, but you're also getting more towards the just chemical weathering dominating. And this is just a plot to kind of like demonstrate that. So if you've got chemical weathering on the vertical axis, physical erosion on the horizontal axis, there are these continents that have these really high mountain ranges over here. They have this really high mechanical weathering, okay, but those are also the ones that tend to have the higher chemical weathering rate. So ultimately, the amount of stuff that's being put into the kind of the aqueous environments where it's available for life is also in part determined by like the tectonic forcing, so the geological cycles. Okay, and this is just to kind of like demonstrate where this is kind of coming out into the ocean. So these are the regions we were just talking about. So the Amazon, okay, so it's receiving lots of, and this is sediment yield. So this is kind of a proxy for the mechanical weathering. But you can kind of also this is highly correlated with the dissolved flux of useful nutrients as well. Okay, so you can see these really high fluxes over in the Ganges, Brahmaputra, Philippines. We have lots and lots of rain, lots of steep slopes. The Yellow and the Yangtze River, I think, in China, huge fluxes coming out, mostly the Himalayas, of elements that are going to be useful to life once they get into the ocean. Okay, to summarise the weathering side of things, so it's the weathering of rocks, and so the interaction of the lithosphere with life is the only really source of calcium, magnesium, potassium, and iron. So these are elements which are critical to life. So if you want to have bones, okay, who doesn't like bones? You need calcium. Okay. If you want photosynthesis to happen, okay, chlorophyll has got magnesium in it. Okay. Iron is also an important element in carbon fixation, in terms of there's an enzyme that helps photosynthesis along the way. It's also important for transporting oxygen around our bodies, why our blood is red. Phosphorus, you know, if you like having teeth, anybody not like teeth? Need phosphorus to have teeth. So these are really important elements, like for our bodies, but also for kind of every cell on Earth, okay, almost. Right? So we need those things, and those really come ultimately from chemical weathering of rocks, and the chemical weathering of rocks is determined by how much mechanical weathering we have. So there's a link to tectonics that are providing all of these goodies that we really need. Okay? And remember, of course, that there are feedbacks. So once we start developing a biosphere, so back in the day, in like the Archean, when it was kind of pretty grim, the flux of maybe chemical webbing to the oceans would have been very different, because we wouldn't have had all of this biology on the land creating soils, okay, helping to increase the flux of nutrients and stuff, elements into the oceans. I mean, there would have been other things happening. We probably would have had like lots of acid rain and stuff like that, but it would have been different, unpleasant and different. Okay, so moving on to the thing that kind of really matters, moving on to us, the biosphere. Okay, so things that are living. It's predominantly made up of carbon, hydrogen, and oxygen. Okay, that's kind of like 99% of us. And it's really determined by photosynthesis. Okay? There is a small amount of chemosynthesis that goes on, so basically so almost all life on Earth ultimately gets its energy from the sun, except for there's a small kind of like amount of kind of biomass. Well, it's actually a large amount of biomass, but it turns over very slowly. That actually gets its energy directly from the chemistry of rocks. Okay, so this is kind of the kinds of crazy life that might exist on other planets. So if you're interested in astrobiology, photosynthesis is kind of like, say, last year. Chemosynthesis is where it all is at. But as far as we're concerned, photosynthesis is critical to the existence of life on Earth. Okay? Once again, it's not true. I mean, we could have life on Earth. It would be pretty boring life. Kind of, we'd be at the kind of like the bacterial level without that, for instance. Anyway, so photosynthesis is important because it provides kind of the base of the food web. Okay? It provides almost all of the biomass which other things eat. But it's also important because it changes the Earth's atmospheric composition. It provides oxygen, which allows larger life forms than just one cell to exist. Okay, so it provides a very energetic molecule, oxygen, which kind of is very useful. Okay. And this is kind of like moving on to kind of some more details of things. So oxygen, carbon, hydrogen kind of make up the bulk in terms of mass of the biomass. And you can see that hydrogen is quite a low percentage there. I mean, it's important in terms of number of atoms. Remember, hydrogen's got a mass of 1. Okay, so in terms of, there are more hydrogen atoms in the biosphere than there are carbon atoms, but carbon is like 12 times heavier. Okay, so that's, I mean, the percentages there are, somewhat arbitrary. Okay, the actual details, so I wouldn't bother remembering those. Just remember that those top 3 are the big guys, and they variously come directly from the atmosphere. It's kind of a little bit controversial where the oxygen comes from in us, whether it actually comes from the atmosphere or the hydrosphere, because we breathe oxygen, yeah? And we also drink water. Okay, both of those have oxygen in. Come on to that in a bit. Carbon comes it does come entirely from the atmosphere, ultimately. Okay? Things we eat are made of carbon, but they get their carbon from either other things they eat or things that have produced, photosynthesized and made carbon out of the atmosphere. And then we've got these other components, okay, nitrogen, calcium, potassium, silicon, iron. Iron's not on that list, but it's a very small percentage. Sulfur. So these are really important things for things like some of the molecules that make up things like DNA, amino acids, cell walls. These are really critical things for life to actually exist at the most fundamental level. They're also important for kind of some of the higher forms of life, so particularly calcium is important, for instance, at the cellular level for energy transport. Okay, you can't move energy around your cell without calcium. You can, it's less efficient. But also if you want to be like a big, complex life form, like a snail, right, you need a shell. It's nice to have a shell. That shell made of calcium carbonate. Okay? So lots of these kind of really critical elements, you can see they're coming from weathering. So they're coming from the biosphere. This is one of the reasons why geology is so important. There are other reasons. Okay? So just to kind of touch briefly on photosynthesis, those of you who have done biology previously at school will realise that this reaction for photosynthesis is wrong. Right, it's a really good approximation. So we take carbon dioxide and water, and we do photosynthesis, okay? Well, we don't, plants do. And they make organic matter, so that's kind of the equation for sucrose, but it's kind of a good approximation for just general organic matter. It's glucose, not sucrose. Anyway, and oxygen. So photosynthesis takes carbon dioxide, water, makes some organic matter, okay? Doesn't, we use that one because it helps the equation balance, and makes oxygen, okay? So it's affecting the atmosphere, producing organic matter. Now, the opposite, of course, is respiration. So it's not like photosynthesis and respiration are not back reactions of each other. They are totally separate reactions. Okay, so you should never write them like that. Okay, you should write them as separate reactions. One goes one way, and then the other one goes the other way. They're not back reactions. Okay, you can't reverse photosynthesis. And so respiration is really important for life because it basically allows higher life forms to exist, because you can basically start to store up energy in organic matter and then make use of that in terms of energy. Okay. So we're going to start moving on to some of these kind of like terminology type things. So there's this terminology called net primary productivity or net primary production, sometimes shortened to NPP. Okay, so that is the gross primary production. Okay, this is the amount of biomass that is produced. Okay, and this is minus plant respiration. Okay, so it's not just the amount of photosynthesis. It's kind of less than the total amount of photosynthesis because some of those plants are instantaneously respiring that organic matter back out. So, for instance, a tree in the daytime it photosynthesizes, but in the nighttime it is respiring. Okay. So the net primary productivity is basically the accumulated production of organic matter by plants in the ocean and the atmosphere. In the atmosphere, the ocean and on land. And I guess there's some terminology here as well. So the heterotroph is an organism that gets its carbon from other organisms, so it eats things, whereas an autotroph is an organism that gets its energy directly from the environment. So, for instance, photosynthesizers are autotrophs. Okay? That doesn't matter so much. This is just to point out that the photosynthesis reactions are actually quite complicated. They're complex, they're not complicated. You don't have to remember all this. This is just ridiculous. But you can see that photosynthesis is just that one reaction taking CO2 and water and producing organic matter. It's actually a series of reactions. The first one requires light, and that takes water, okay? And then there's this adenosine triphosphate thingy, and that uses phosphate and light and splits that water into hydrogen ions and oxygen. Okay? So that's the first part of photosynthesis. And then there's a second part of photosynthesis that takes that energy that is released, and that takes those hydrogen ions, okay, which are this reaction here, and they attack the CO2. Okay? And they attack the CO2 and they take the CO2, they rip it apart, and they produce organic matter. Okay? Like that. So the details aren't so important, but you can see here that actually the oxygen in organic matter is not directly coming from the water. Okay? So it looks like in this reaction the oxygen in the organic matter is actually coming from CO2. Okay? So it's not it's more complex than that, but just to point out that the simple CO2 plus water goes to organic matter and oxygen. It's a really simplified version of photosynthesis. It's really good for getting kind of like understanding the broad picture, but the details are much more complex. So the role of temperature in the biosphere, you can see here that as you increase temperature, primary productivity goes up. So the hotter it is, the more active the biosphere is. Similarly, the wetter it is, the more active the biosphere is. So things like, think the tropical rainforests, hot, wet, produce lots of organic matter. Okay, but we also need all of these elements, nitrate, phosphate, all these other things. And that's what the following kind of like lectures will be about. And I guess now I think I'll mention this in terms of internal cycling. So if we add to the system a little bit of kind of rock-derived nitrogen or rock-derived phosphorus, that doesn't just get used by plants once. Used by the plants, plant makes some organic matter, it's got nitrogen, phosphorus in it, and then that plant dies, and then we have to get some more from the rocks. There's this concept of internal cycling or recycling of nutrients. So if we added into this kind of like cartoon here some nutrients, some nitrogen or phosphorus, we could like grow some trees, but those trees will die, and as they break down and kind of like get eaten by fungi and all that kind of stuff, they'll release those nutrients back into the local environment so they can be used again and again and again and again. So actually the nutrients can be basically recycled many times, okay, before they're kind of exited out of the local system into the like washed away in rivers and stuff. So this concept of how efficient that internal cycling is really important for determining how much life can go on. Okay? Because if you don't efficiently use your nutrients, then you have much less life going on. Okay? So go on and talk a little bit now about where this kind of like life is happening. So on the land, okay, so this is the net primary productivity, so red is like lots and lots of life going on. If you just look at the land here, you see we're really limited by the availability of water. Okay, so regions that are dry, so Patagonia, it's in the middle there at the bottom, in Argentina, Saharan Africa, very southern tip of Africa, central of Australia. These are famously dry places. Okay, so there's not a lot of biological activity going on there. Not a lot of material being produced because there's no water available for that photosynthesis. Whereas in the wet places, like the Amazon basin and the Congo basin and Europe, lots of wetness here, so we can get lots and lots of primary productivity. So in the ocean, okay, if you now look in the ocean, you're never limited by water in the ocean because it's made of water. But we are limited by other things. So you can see here that we're not getting the same level of productivity in the ocean compared to the land. So even though we've got loads and loads of water, okay, so you just look at the Amazon there, we've got nowhere near the amount of productivity in the ocean we do on land. And that's not because we're limited by the amount of water, or the other thing you might be limited by, it might be dark. Okay, so in the polar regions you might not get productivity because it's dark, so light limiting. We're limited in the oceans usually by the availability of these key nutrients, nitrogen, phosphate, iron. They're just not available. There's not enough of them dissolved in the water because they're coming from the land mostly. Okay? You might have lots in the ocean in the coastal zones, but as you get out into the middle of the ocean, you're too far away from the land. All the nutrients have been used up by life, and then that life has sunk to the bottom of the ocean, taking the nutrients with it. So once you get out into the middle of the ocean, although you've got loads of water, you've got loads of light, you've got lots of carbon dissolved in the ocean, okay, you cannot use it, okay, because you're running out of nutrients. So it turns out the distribution of nutrients in the ocean is really important for determining how much primary productivity you can get in the ocean. And that's important because half of the global, so it's half of the primary productivity is in the ocean, that's where it's limited by the availability of nutrients. Okay? And the ocean is a lot bigger than the land, so there's much more potential in the ocean for changes in the amount of primary productivity. Okay? But we're limited by the availability of these nutrients. Okay? And it's really heterogeneous. Right? So in some places we get almost no biological activity at all. So right in the middle of the Pacific, okay, in what we call ocean gyres, where they're basically isolated from the coasts by the circulation of the ocean, we get almost none. Whereas in coastal zones where we're really close to these nutrient sources, we can get rates of primary productivity that are even higher than in tropical rainforests. Okay, so super high productivity, lots of carbon being drawn down into organic matter. And we'll go on to see why that is in the next lectures. And I just point back to this figure here to give you an idea of the kind of fluxes we're talking about. So the biosphere, marine and terrestrial, is really active. It's a huge flux of carbon out of the atmosphere every year. So 100 gigatons of carbon a year, comparing to the amount that we're burning. Okay, so we're up at maybe about just under 10. Okay, so it's a huge, huge flux. Okay, that's only the flux out. Okay, so there is also a return flux. Okay, so the biosphere isn't continually accumulating organic matter. Almost equal amount of carbon is being released from the biosphere by the decay of dead trees, plants, decaying organic matter in soils. That's releasing that carbon back into the atmosphere. So actually the net flux out of the atmosphere is much, much smaller. It's only maybe a few 5 or so gigatons of carbon a year. So some of this emissions is offset by this biosphere activity, but it's only a small component of the overall biological current cycle. So this is a really, 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 really big flux of carbon each year. So kind of briefly, the hydrosphere kind of made up of kind of like the wet bits of Earth, mostly the ocean. The cryosphere, so ice caps and stuff, is quite a big component of the total amount of fresh water on Earth. It's not really so important for the biological activity because it's frozen. But we have all these other things. So obviously groundwater doesn't have a lot of life going on in it because it's underground, so it's isolated from the atmosphere. Can't get any photosynthesis going on it. But lakes, very important, lakes and rivers, because they have lots of nutrients in them, because they're directly interacting with the lithosphere. So briefly, the ocean is kind of a big guy. Okay, so it's the most important part of the hydrosphere in terms of life because it is literally massive. But it's got this kind of structure to it where the surface layer of the ocean, you will hopefully recall from is heated from above. The sun heats the surface of the ocean, warms it up, okay, compared to the deep ocean underneath. That makes the surface layer of the ocean less dense than the ocean underneath. Okay? That keeps it very well stratified. So we have a buoyant surface layer, okay, and then a more dense deep ocean, and that inhibits mixing between the two. So that means that if you've got, for instance, if you have, so this is the surface ocean up here, this is where light is, okay, very little light makes its way down to even 500 meters, 1,000 meters in the ocean. Okay, so this is where life would like to happen, okay, but this part of the ocean typically has very, very few nutrients in it because any life that happens up here produces particles, like bits of animal, right? These then, when they die, they sink down into the deep ocean, okay, and get respired, degraded by bacteria, and release their nutrients in the deep water. So this means that the ocean as a whole actually has loads of nutrients in it. Loads and loads of nutrients. But they're all in the deep water at the bottom. Okay? And because the ocean is thermally stratified, because the top layer is really a lot less dense than the bottom layer, it's really hard to mix the water between the two layers. So that means that even though the ocean as a whole might have lots of nutrients in it, the surface ocean, you can kind of think of that as a separate box. Okay, you can think of the ocean as just two parts, a deep part and a shallow part. The shallow part doesn't have very many nutrients in, but it has lots of light. Okay, and the deep ocean has got loads of nutrients in it, but it has no light. Okay, so if you keep that situation, you get no life. So you tend to get life existing in the oceans when these two layers are forced to mix together. Okay, so you have an extremely big storm, or you have coastal upwelling. Okay, you can mix these two layers together. Okay, and when that happens, you mix together. You've got one part of the ocean that's got missing a key thing, and another part of the ocean that's missing light, and you mix those together, and you're suddenly missing nothing, and you can have life. Surface currents blow things around. Just point out that the deep ocean is actually connected to the atmosphere, but only at the high polar latitudes, where deep water can sink down to the bottom. Now, annoyingly, this is an important concept. We have 5 minutes to cover it, so that's my fault. There's this concept of residence time. So, residence time of a thing that's dissolved in the ocean, okay, is a description of the average amount of time any one atom of that substance is actually in the ocean before it's removed. Okay, so if you think of this as an example, imagine that box, that reservoir, is the whole ocean. Okay, and we've got a flux of something coming into that ocean. Okay, so rather than think of a flux of just water flowing into the ocean, think of it the flux of dissolved ions. So maybe the flux of calcium dissolved in rivers. Okay, so that's introducing more and more calcium into the ocean. Okay, now the flux out. Okay, it's not the flux out of water, we're thinking of the flux of calcium. So the flux out here is how is calcium removed from the ocean? It's removed by the formation of shells, corals, okay, things like that are producing things made of calcium, and they're sinking out and sitting on the seafloor. Okay? So the residence time is the average amount of time any one calcium atom is dissolved in the ocean, okay, before it's ultimately removed by that precipitation as calcium carbonate. Okay, so that can be described by this thing called the residence time. So if we just, to very simply work that out, if we worked out the total amount of calcium dissolved in the whole ocean, okay, in terms of kilograms of calcium, and then or moles of calcium, and then we knew the input flux, how much calcium is being added per year. Okay. Now, if we just divide the mass by the flux, you can work through the units there, and you can work out that that will give you units of per time. Yeah, or time. Okay. See, another way of thinking about it is looking at the what would happen if you suddenly stopped one of the fluxes. So if you stopped rivers putting calcium into the ocean, how long would it take for the concentration of calcium in the ocean to reduce by half? Okay? If you kept the flux of removal by production of shells constant. Okay? So try and think of it like that. I'll try and put a better description of this on the web while I'm talking over a video or not. Because I haven't reached the end of the lecture. And it's the end of the lecture. So bring stuff to the practical that you've done. That would be useful.